I suppose this all goes back to I went to a summer school in Lyon that was organised by Philippe Gilles, at which Brian Conrad gave a series of extremely lucid and engaging lectures, and as a result of that, I decided it might even be possible to say something about pseudo-reductive groups after having seen those talks. So this is one of the things that we were able to do as a result of that. Okay, so I will kick off. Let's have a drawing thing. So I'm going to let K be a field, and this field is going to have characteristic P, which ought to be bigger than 0. I may as well just set that for all of this. No doubt I'll say something that might be true for characteristic 0, but it certainly won't be interesting in the context of anything that I'm going to say now. And even for the most part of this talk, I'm going to want K to be imperfect. So that's going to be an important part of this, as we'll see. And the objects under study are going to be affine algebraic groups. So let G be an affine algebraic group over K. Let me just unpack that slightly. I know that people come to algebraic groups from different points of view. In the traditional way that you learn about these is by thinking about these as varieties over algebraically closed fields, and then you can dispense with, to some degree, you can dispense with having to think about these things scheme theoretically. But for the purposes of this theory, where K is not algebraically closed and G may not be smooth in some instances, or at least many of the subgroups that are important won't be, you want to be thinking scheme theoretically. So let's just set up some basic notation. I'm going to let X be a K functor. That's going to mean that if X is just going to have to be a functor from K algebras to sets. So that's what I mean by a K functor. And then G is going to be a K group functor if it's a functor from K algebras to groups. And I want to not look at all K group functors, but affine ones. So here I'll just say that K is affine for me. So K is an affine scheme, so of finite type. I suppose I should say finitely presented as well, but anyway, K is going to be an affine scheme if, for the purposes of this talk, if it's the following. So if it is representable by a finitely presented K algebra, which I might denote something like that, Kx. So that means that there is a natural isomorphism of this functor with the following, the homomorphisms as K algebras from this particular K algebra to blank. So we'll obviously get a set here if I put a K algebra in, and so that's what I mean by an affine scheme. And so I'm going to be looking at affine algebraic groups that are going to just be affine K group functors under that definition. I'm going to be interested in representations of these things. So let's start with So let V be a K module. So K is a field. It is possible to work with more general rings. Some of the theory will go across, but I'm sticking to the case where K is a field. So that just means that V is a vector space. I do not insist that the vector space be finite dimensional. In fact, for the proof of many of the results, we need to work with infinite dimensional modules. Right. But let's define what an action is first, and then I can define what it means for this to be a representation. So we say G acts on X. So if this is a K group functor, this is a K functor. If there's a natural transformation from G cross X to X, so that whenever I plug in a K algebra A, I'll get a map from a group cross a set to a set. This needs to be a group action. That's normal. Right. And so if I've got a K module, I can turn this into a K functor in the following way. So, so define a K group functor, sorry, yes, it is a K group functor, VA, by what does it do to a K algebra? Let's just put one in. It needs to give me a K group. Needs to give me a group, and this is the group it's going to give me. So it's just tensoring. Sorry, that should be a V. Let's try the eraser. Very nice. Right. So I just tensor my vector space with this K algebra, and then we say that V is a G module if G acts on VA via this process in such a way that it's alinear. By alinear automorphisms. Right, so that's what a G module is going to be. In other words, a representation of G. If V is finite dimensional, it will probably be reassuring to know that that's the same thing as getting a homomorphism from G into GLV. So that's in fact the same thing. Right. Okay. So here's my problem. Classify all the irreducible representations of G. So in other words, all the G modules. So I'll just try and put that in a box. Right, so a couple of comments. First of all, that since we're over a field, we have a property of local finiteness. That means that if you generate in any representation, you generate from a single vector, you take the smallest submodule containing a single vector, then you get something that's finite dimensional. That means in particular that any irreducible representation of this group is going to be finite dimensional. So that's a good thing to know. I am going to want to put two conditions on my group. So I'm going to ask that G is smooth and that G is connected. But it's interesting just to think about what you'd have to do if you wanted to drop either of these conditions. So let me just say a little bit about this. If you want to drop the notion that G is smooth, then you have to deal with the infinitesimal algebraic groups in particular, and in particular you might you will have to deal with height 1 group schemes. So relaxing this, relax takes us into the world of irreducible reps of restricted Lie algebras. And this is a huge theory in its own right, probably starting with Chang in the, I can't remember when it was, but quite a long time ago, who classified the representations of the Witt algebra W1. So this is the Lie algebra that's generated by the following elements. So that's actually a basis under these commutator relations. So x the I del, x the j del is equal to so j minus I times x to the I plus j minus 1 del. There are many people who have contributed to that theory. It would be too difficult to list them all, but I just wanted to advertise that my student, so many people, certainly Holmes did a huge amount of work on this, and I just wanted to advertise that my student Horatio Guerra has been able to classify the representations of the last remaining Hamiltonian algebra in rank 1. So that's one piece of the theory that you would need to look at if you wanted to drop smooth, and if you wanted to drop connected. So to drop connected, then you need to think about the representations of all finite groups, because this will be a finite group, and well, we have plenty of finite groups. So e.g., what is the character table of E8 of Q? And this, of course, is a massive problem that takes you into de Lie and Lustig theory. And further, I think I was at a conference in Cambridge just before everything got shut down, and Meinolf Geck has been able to make some very important progress on this problem. He was able to announce, which is very interesting. Right, so that was all parenthetical. We're going to look at the case where G is smooth and connected, and pseudo-reductive groups are going to come up in that discussion. Right, so what is a pseudo-reductive group? Well, let RUK of G, so this is going to be a subgroup of G, and it's going to be the K unipotent radical, and it's going to be the largest smooth connected normal unipotent K subgroup of G. It'll automatically be closed as well by virtue of this largest aspect. So what's unipotent mean? Unipotent, so U is unipotent. So if you use an affine algebraic group, it's unipotent if it is isomorphic to a subgroup of the upper triangular, so upper unitriangular matrices, unitriangular matrices of some GLN. So some subgroup of this. Okay, and then having defined what K unipotent radical is, we say that G is pseudo-reductive if it's smooth and connected, and the K unipotent radical is trivial. So a small amount of history about this. They were first considered by Jacques Tietz in a series of lectures in the Collège de France in the 1990s, I believe. That was all that was said about them for a long time, and they lay dormant until some major work of Brian Conrad, Ofer Gaba, and Gopal Prasad, who is joining us on Indu's iPad. So the first book set out the general theory, showed that almost all pseudo-reductive groups can be obtained by a certain standard construction, and they also, so the first and third authors, so let me write them all down. So Conrad, Gaba, Prasad, and the first and third authors continued on to give a complete classification of pseudo-reductive groups. So complete classification of pseudo-reductive groups. Right. Okay. So I think by virtue, so in order to give a little bit of motivation, one of the reasons that that this book exists is because Conrad was proved that the Tate-Shafarevich groups and Tamagawa numbers for smooth connected affine algebraic groups are always finite, and that took him naturally to have to make and prove statements about pseudo-reductive groups. So they came up very naturally there. I barely understand. In fact, I don't understand at all any of those words that I've just said, but I can give you a much more simple-minded motivation for why pseudo-reductive groups should be interesting based on the problem that I have just stated. So let me first recall that a unipotent group has only one simple module up to isomorphism, and that's the trivial module K. So this is a well-known result that you can find in Demasieux-Gabriel, for example. So if I have if U is a unipotent group and it's normal inside any affine algebraic group G, and V is a simple G module, then, as we've said, V has to be finite dimensional. If I restrict the action of G to U and look at the resulting U module, what I'll get is a finite dimensional module which will have a Jordan-Holder series, and all of the composition factors in this must be trivial modules, because those are the only simple modules for a unipotent group. So it must have some fixed points, specifically the socle of the action of U on V. So this is non-zero. But because U is normal in G, it's also a G submodule. But as VU is a G submodule, it must be the whole thing, because we assume that it's a simple module. So V of U is equal to V, and therefore U is in the kernel of the action of G on V. So action of G on V factors through through G over U. So what that means is, if you start with a smooth connected affine algebraic group, then its K unipotent radical will be in the kernel of its action on any irreducible module. And therefore, we may as well assume that it's trivial. In other words, that we have a pseudo-reductive group. So, may as well assume G is pseudo-reductive. So this gives a very clear motivation for why pseudo-reductive groups should be interesting. Right. Let's have an example of a pseudo-reductive group. So I'm just going to follow the narrative that one finds at the beginning of CGP, and the major way of producing pseudo-reductive groups is via Weil restriction, and specifically across an inseparable extension. So let's just talk about Weil restriction briefly. So one could do this in much greater generality, but I'm just going to look at the case where I have a field extension. And if G is a K-dashed group, so it's defined over K-dashed, Weil restriction produces you a new group over this smaller field. So can produce a new group R K-dashed over K, so this is the notation for it, restriction across this field extension of G, and this is called the Weil restriction of G across this field extension. It needs to be a functor from K algebras to groups. So how does that work? So if I plug in the K algebra A, well, I've not got very much to play with. So it had better be something. It had better be something to do with G. And I know that G can only take values in K-dashed algebras. So I need to turn this algebra A into a K-dashed algebra somehow. And there's one obvious way to do that, which is this. Just tensor it up with K, no, over K with K-dashed. And then you get a K-dashed algebra, so then you can plug into G. This is a rigorous definition, but it is not very good for trying to understand, trying to get any intuition about what this Weil restriction looks like. A very nice a very nice example, which you can visualize, is to think about what happens if you take the complex numbers, the multiplicative group of the complex numbers, and do a Weil restriction from that to the real numbers. So you can see that if you plug in the just the field k itself, then you're just going to get g of k dashed. So the k points of this group are the same as the k dash points of G. So really what we're doing is we're just trying to look at the group G as a k group, but without somehow changing the points of it. So let's do this with the multiplicative group of the complex numbers. So just think of an Argand plane, which obviously has the 0 missing, because we're looking at the multiplicative group, and think of that as a real group. So it's going to be twice the dimension, because the complex dimension is 1, so the real dimension is going to be 2. And there are two interesting subgroups. One is the real line minus the point at 0, so the multiplicative group of the real numbers. And another interesting subgroup are all the complex numbers of modulus 1. So, and if you put those two things together, you do get the complex plane minus the origin. So if I look at this, I'm going to get multiplicative group of the real numbers. I'm going to get those of modulus 1, that's an S1, and they intersect though, so they intersect at plus or minus 1, so I need to factor that out. So this is isomorphisms isomorphic to are bigger than 0 cross S1. So this is sort of like polar coordinates. So that's the game that we're playing with Weil restriction. In fact, this exact same example, just done over an inseparable extension, will give you a pseudo-reductive group, which is not reductive. So now let k dashed be equal to k adjoin t, where t to the p is in k, but t is not in k. So this is a sort of archetypal inseparable extension, and let g be equal to the Weil restriction across this field extension of the multiplicative group of k dashed. Then we claim this is pseudo-reductive, but not reductive. So why is it pseudo-reductive? Well, fortunately in this case we can see that the k points are dense, so I'm just going to argue from the point of view of the k points here. So g of k are just the k dash points of Gm, so it's just k dashed star, a multiplicative group of that field. Observe that this doesn't have any unipotent elements at all that are non-trivial. So what does a unipotent element, so if it has any unipotent elements, it's going to have, we're going to have to be able to solve this equation. So it will have elements of order p. But since this is a field of characteristic p, we can factorize it using the student's binomial theorem to get x minus 1 to the p is 0, which, because we're a field, implies that x is 1. So this doesn't have any unipotent elements whatsoever. So it certainly can't have a unipotent radical, and so it is pseudo-reductive. but it's not reductive. And to see this, we want to consider what happens to this group under the p-power map. So apply p-power map. So x maps to x to the p. Well, the elements in here are quotients of polynomials in, well, in fact, they're just polynomials in t over k. When I take those things to the power p, the power p distributes all the way through, and I get things that are instead polynomials in t to the p. So I must be, which is already in k. So this pushes k dashed into k. Now, in this group, there is a canonical copy of the multiplicative group of k in here. And so, because this p-th power map pushes us into that, if I factor it out, this k subgroup, the subgroup that's isomorphic to k star, I must just get 1. So G over the canonical copy of Gn is now unipotent. And I know what the index of these fields are. In fact, it's of dimension p minus 1. So could it be reductive? Well, to decide if it's reductive, we have to base change up to the algebraic closure and then see what its unipotent radical is. But if I give you a group which is reductive, then you know precisely what its structure is. It's a central product of simple groups and a central torus, and so certainly it does not have any unipotent quotients. So there is absolutely no way that this thing could be reductive. So reductive groups do not have unipotent quotients. Okay, so that's an example. Right. So I feel like I'm going to head massively over time if I don't speed up here. One of the things that we need to know is the following. So an important result of CGP is a theorem which says that if G is pseudo-reductive and pseudo-split, then G has a Levy subgroup M. So let me just explain what that means. So pseudo-split means that there's a maximal torus which is split. So G has a split maximal torus, and contained in M, and that means that if I base change to k bar, so to be a Levy means that you complement the geometric unipotent radical. So the base change to k bar decomposes in that way. Okay, that's important. This is a reductive group, split reductive group, because it contains a split maximal torus. And we know a lot about the representation theory of split reductive groups. In particular, if we choose a Borel inside here, then it will have it will define a collection of dominant weights, and those dominant weights parameterize the simple modules for this group. So our theorem is to say that in fact the same is going to be true for pseudo-split, pseudo-reductive groups. So this is the theorem. The irreducible reps of G are in one-to-one correspondence with the irreducible reps of M, which are in one-to-one correspondence with the dominant weights of the torus xt plus. So furthermore, I can tell you what the dimensions are. So if LG lambda is the corresponding simple representation for G with dominant weight lambda, then the dimension of that is equal to the dimension of Lm of lambda times Lc of lambda, where C, which is the centralizer in G of T, is a Cartan subgroup of G. So it's a fact of the theory of pseudo-reductive groups that Cartan subgroups of pseudo-reductive groups are themselves pseudo-reductive. They're commutative. And so in order to see that this, this dimension, in order to see that this makes sense as a piece of notation, just run the earlier part of this theorem again. So here, the irreducible representations of a commutative pseudo-reductive, pseudo-split pseudo-reductive group will be in one-to-one correspondence with the irreducible representations of its levy, which will be this maximal torus, and those will just be in one-to-one correspondence with all the weights of T. So this notation makes sense. Right. Let me make a couple of comments about this formula. This is, so here we have a factor which is telling us about the dimensions of simple modules for split reductive groups. This is a major area of research. It's still ongoing. There are methods for calculating these things using Janssen's sum formula and the other algebraic techniques like Steinberg's tensor product theorem, the linkage principle, and so on. There was a conjecture for a long time that the dimensions of simple modules are essentially determined by the Kazhdan-Lustig polynomials. So this was Lustig's famous conjecture. It was proved to be true for extremely large characteristics relative to the size of the root system, and widely expected to be true in general. It is not. And Geordie Williamson has done a huge amount of work providing counterexamples and proposing other means of trying to understand what these numbers should be. So the current state of play, as far as I understand it, is that there are now P Kazhdan-Lustig polynomials. The problem with those is that they're extremely difficult to calculate, and I think they've only been calculated for SL2, where of course these numbers are very easy to work out anyway. So this is still a huge area of research, and work is ongoing. This factor, we're interested in the dimensions of simple modules for commutative split pseudo-reductive groups, and not very much has been done at all on trying to understand those. I guess you wouldn't do unless you were interested in these in the first place. I should say that there is a result of Michel Briand, which attaches a field to the irreducible representation of any commutative algebraic group. So it's a very general result, but it doesn't tell you very much about the dimension. You would have to know quite a lot more about the structure of your commutative algebraic group. But we have one more theorem, and I'll finish with this, which is so this is again joint with Mike. That says that, and I'll just write it in the following way. We know the dimension of LC of lambda when C is a product of Weil restrictions of GM across purely inseparable field extensions. So they would have to be purely inseparable field extensions if you're doing Weil restrictions, because otherwise you won't pick up. So the resulting group you would get by doing a Weil restriction would not be pseudo-split. We understand that situation. It comes down to looking at the p-adic decomposition of this weight and understanding how that interacts with the structure of the fields that you're doing these Weil restrictions across. But one thing that we can do is give a complete description when the rank of C is 1. So this leads to a complete description, well, as complete as we can manage, of the dimension of LC of lambda when C has rank 1. And I think that would be a good place to stop.
Are there any questions?
So very nice talk, David. This is Gopal from Ann Arbor.
Hi, Gopal.
How are you?
I'm very well, thank you.
Okay, I'm Philippe. So I managed to connect. It was not so easy, but okay. I attended the talk. Can you? Is one of the way of your main theorem, which is easy to see? I mean, one direction of the correspondence.
Right. So I think probably the easiest thing is for me to just give you a very basic sketch of the proof. So how do you produce representations? You induce. So one considers the induction from the Levy subgroup to G of what we understand very well. I say very well, but we at least can parameterize them. We know where to find these simple modules for reductive groups in themselves. The inductions of from the Borel of one-dimensional representations. So you want to consider this thing, and there are various results which tell you how these inductions behave under base change. So if you base change the algebraic closure, then this thing at the top will then decompose as a semi-direct product of the base change of M and a unipotent radical, and you can use that fact to understand it, to understand the structure of this better. What turns out to be the case is that this has a simple socle. And once you know that, you can run a Frobenius reciprocity argument to show that there has to be some. So there has to be some submodule LG of lambda which sits in the middle, sits at the bottom of this induction, and you then want to see that it's unique up to isomorphism, and that takes a little bit more work. There's inductions galore is the basic idea, but I think that does answer your question. Where does this thing come from? It's the socle of this infinite dimensional representation. So
okay. No,
yeah.
Okay, sounds good. So that's the reason why you started with this infinite dimensional business. I see. Thank you.
Yeah, yeah. There were some interesting results working with inducing from in such a way that you end up with infinite dimensional representations. For example, so there's a lot of work of Bendel, Nakano, and Pillen where they study very carefully the induction functor from the finite group of Lie type with just the FQ points of G with a representation of over obviously its defining characteristic. So I don't know how just leave it as L. In fact, you can just do this with K, and you get as much information as you want, and they can prove very interesting things about the fact that this has a certain filtration, which whose sections they can describe very carefully, and so they can transport a lot of information about the representation theory of the algebraic group that we know quite well, because there's quite a lot of geometry here down to the finite group. So yeah, I mean, working with infinite dimensional modules that you get by induction is definitely worth doing.
So are there any other questions? Well, let's thank the speaker. Let me see if I can unmute everyone.